Hello everyone, I welcome you all. Now I am going to explain parallel and counterflow heat exchanger apparatus in our heat transfer laboratory. The main aim of this experiment is to find out the overall heat transfer coefficient of double pipe heat exchanger both parallel and counterflow conditions. So, come to the experimental description. This one is the heat exchanger setup. Here two tubes are arranged concentrically. Inner tube is made up of copper and diameter of inner tube varying from 19 mm to 25 mm. Outer tube is made up of stainless steel. The diameters varying from 36 mm to 39 mm. Four valves are provided on both sides of the heat exchanger, two for the cold water and two for the hot water. Here one insulation is provided on the outer surface of the outer tube to resist the flow of heat from heat exchanger to the atmosphere, and two rotameters are provided here. One is for hot water and one is for the cold water. Here by using the rotameter to measure and adjust the flow of water into the heat exchanger, and two console switches are provided here. One is for hot water and one is for the cold water. One geyser is provided here for the to give the heat input to the water. So here hot water is flowing inside the tube, that means flowing into the copper tube, and cold water is flowing in between the copper tube and the stainless tube. By using this temperature indicator and the channel selector, monitor the temperature readings at both sides of the heat exchanger. Four thermocouples are provided at two sides of the heat exchanger, so that temperature readings are monitored by using the temperature indicator and the channel selector. So let us go for the experimental procedure. Let us go for the experimental procedure. I am giving the power supply to the equipment. Tripper on. So release the, first of all release the wall, connected from the water reservoir. So after releasing the wall connected from the water reservoir, adjust the mass flow rate of the hot and cold water by using the rotameter. After adjusting the mass flow rate of the water, here observe here, this one is the inlet and this one is the outlet of the rotameter. From the outlet of the rotameter, one pipe is directly connected to the geyser. This one is the inlet to the geyser and this one is the outlet to the geyser. Another pipe is connected from outlet of the geyser to the inlet of the copper tube. So here this one is the hot water setup. So hot water will enter in this side into the heat exchanger, flow along in this side, and this one is the cold water setup. This one is the outlet of the rotameter, cold water rotameter. This outlet of the cold water rotameter pipe is directly connected to the stainless steel pipe. Here again cold water will entering in this side. So cold water flowing along in this direction. Here hot water is flowing in this direction and cold water is also flowing in this direction. Both fluids are flowing in the same direction. So the system is in parallel flow condition. Switch on the console. Observe the temperature readings here, inlet and outlet temperatures. By using this channel selector and temperature indicator, monitor the temperature readings. Here T1 indicates that cold water inlet temperature and T2 indicates that cold water outlet temperature, and T3 indicates that hot water inlet temperature. T4 indicates that hot water outlet temperature. So monitor the temperature readings. Wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, tabulate the values and go for the experimental calculation of parallel flow heat exchanger. These are the values recorded during the time of experimentation in parallel flow condition. Initially, I given the mass flow rate of the cold water and hot water by using the rotameters as 0.5 liters per minute and convert this into the kg per second, is 8.33 into 10 power minus 3 kg per second. The hot water inlet temperature and outlet temperature and cold water and inlet temperature and outlet temperature values are tabulated after reaching the steady state condition. These are the tabulated values, and this is the heat exchanger setup. This one is the inner tube, that is the copper tube, and this one is the outer tube, that is the stainless tube, and this one is the inlet of copper tube, outlet of the copper tube. This one is the inlet of stainless tube, and this one is the outlet of stainless tube. Observe here, the hot fluid is flowing along in this direction and cold fluid also flowing in this direction only. Both fluids are traveling in the same direction. So, the setup is in parallel flow condition. This is the temperature profile of hot and cold fluids. Initially, hot fluid temperature is high, and at the outlet of the heat exchanger, the temperature of hot fluid will be low compared to initial value. At the outlet value will be low because it will lose the heat. And come to the cold fluid, initially cold fluid temperature is low, at the outlet of the heat exchanger the cold fluid temperature will be high because it will absorb the heat from the hot fluid. Compared to initial value, final value will be high. So, come to the calculation part here. This is the expression for total rate of heat transfer within the heat exchangers, Q equal to UA Here Q is the amount of heat transfer within the system and U is the overall heat transfer coefficient. We need to find out that one. A means surface area of the heat exchanger, and LMTD, this one is the log mean temperature difference. We need to find out by using this temperature profile. First of all, find out the rate of heat transfer Q by according to the energy balance equation. Total rate of heat transfer within the heat exchanger is equal to the heat energy lost by the hot water is equal to the heat energy gained by the cold water. Calculate, I am rewriting this equation. mCp delta T of hot water equal to mCp delta T of cold water. Calculate Q value by using this equation or this equation. Here I am using this equation. Q equal to mass of the hot water into specific heat of hot water into temperature difference. That means hot fluid inlet minus hot fluid outlet temperatures. Substitute the values here. Mass of the hot water is 8.33 into 10 to the power of minus 3. Specific heat of hot water is 4187 joule per kg degree centigrade. Temperature of hot water inlet and temperature of hot water outlet 51.2 minus 46.3. Calculate this value by using the calculator. It is 170.84 watts is the rate of heat transfer Q. So, let us find the LMTD by using the temperature profile. The formula for log mean temperature difference is delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2. Substitute the values here. Minus delta T2 means difference between hot fluid outlet temperature minus cold fluid outlet temperature divided by ln of Thi minus Tci divided by Th naught minus Tc naught. So, that equal to, substitute all the values here. Thi 51.2 minus 30.9 minus of Th naught 46.3 minus Tc naught 37 divided by ln of 51.2 minus 30.9 divided by 46.3 minus 37. Calculate this value by using the calculator. (14.09 degree centigrade is the LMTD. Substitute this LMTD value and Q value in this equation, we will get the overall heat transfer coefficient. Overall heat transfer coefficient U equal to Q. Q means 170 point. Here area, here we need to substitute the surface area of heat exchanger. Here heat is transferring through the surface of the copper pipe. So here I am substituting the diameter of the copper pipe, pi into diameter of the copper pipe 0.025 meters to length 1.1 meter is the length of the heat exchanger into LMTD. LMTD value just now we calculated 14.09. Calculate this value. Overall heat transfer coefficient in parallel flow heat exchanger is 140.34 watt per meter square degree centigrade. Thank you. After conducting the experiment in parallel flow condition, I am changing the inlet and outlet walls of the heat exchanger, inlet and outlet walls of the cold water tubes. So now I am switch oning the console. Observe here, this one is the cold water inlet and this one is the cold water outlet, and this one is the hot water inlet and this one is the hot water outlet. Water is flowing in this direction, cold water is flowing in this direction, both fluids are flowing in the opposite direction. So the system is in counterflow condition. At the time, again monitor the temperature readings here, wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, tabulate the values and go for the experimental calculations. These are the values recorded during the time of the experimentation for counterflow condition. This one is the heat exchanger setup. This is the temperature profile of the both hot and cold fluids. Initially, the temperature of hot fluid is high, and at the end of the, at the outlet of the tube, the temperature is low compared to the initial value. Come to the cold fluid, initially the cold fluid temperature is low, at the outlet of the tube the cold fluid temperature is high compared to the initial value, because the cold fluid will absorb the heat from the hot fluid. Here hot fluid will lose the heat to the cold fluid. So the temperature difference between these two is called the delta T1, and the temperature difference between these two is called the delta T2. So the delta T1, delta T2 values are calculated. We know that rate of heat transfer within the heat exchanger is Q equal to UA LMTD. Here Q means total rate of heat transfer within the heat exchanger. U means the overall heat transfer coefficient. We need to find out the overall heat transfer coefficient. A means the surface area of the heat exchanger, and LMTD means log mean temperature difference. This value is calculated by using the temperature profile, and first of all calculate the Q value. Before going to the Q value, first of all calculate the area value. Here we need to find out the surface area. The formula for surface area is pi dl. Here heat is transferring along the copper pipe surface only. That's why I substituted the diameter of the copper pipe, that is 0.025 meters, and 1.1 meter is the length of the heat exchanger. So the area is 0.0863 meter square. Find out the rate of heat transfer Q. Total rate of heat transfer within the heat exchanger is equal to the heat energy lost by the hot water is equal to the heat energy gained by the cold water. Calculate the Q value by using this form or calculate Q value by using this form. Here I am considering the hot water. Rate of heat flow Q equal to, we know that how to find out the amount of energy transferred to the from the hot water, mCp delta T of hot water. Here mass of the hot water already calculated, 8.33 into 10 to the power of minus 3. We know the specific heat of the water 4187 joule per kg degree centigrade. Temperature difference, hot water inlet and outlet temperatures 50.9 minus 46.8. Calculate this value by using the calculator. 142.94 watts is the, find out the LMTD. We know the formula for LMTD. LMTD equal to delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2. Already delta T1, delta T2 values are calculated. Substitute the values here. 13.8 minus 12.9 divided by ln of 13.8 divided by 12.9. Calculate this value. 13.34 degree centigrade is the LMTD. Substitute this LMTD, rate of heat flow Q, area in this equation, we will get the overall heat transfer coefficient. U equal to 142.94 divided by area 0.0863 into LMTD just now calculated 13.34. 142.94 divided by overall heat transfer coefficient U equal to 124.16 watt per meter square degree centigrade. This is the overall heat transfer coefficient value in counterflow condition. Thank you.